Welcome to the presentation Monitoring Water Quality with the Spectrophotometer, a proof of concept of a smart buoy. This paper deals with marine fisheries and aquaculture, which are fundamental sources in life and development of many countries. Real-time monitoring of environmental conditions of marine aquacultures allows targeted interventions to maintain the health of fish species and of the marine environment. This paper is a proof of concept of a smart buoy to monitor the quality of water in IoT deployments. The buoy is connected to the internet by a LoRaWAN link that transmits data acquired by a spectrophotometer that in principle allows us with a single sensor to obtain multiple parameters of water quality. This prototype solution is aimed at those countries which, despite being their economies based on aquaculture, they do not have expensive or sophisticated technologies. The ocean makes an essential contribution to the worldwide economy, offering jobs to hundreds of thousands of people. Nevertheless, we are witnessing persistent overexploitation of marine resources. Aquaculture production is one of the sectors with the most significant growth perspective. Aquaculture production is rising, while wild capture production is almost stable. However, marine and aquatic ecosystems are under stress. Global fisheries and aquaculture could be more productive and sustainable if they were optimally managed. Some of the most important quantities to monitor water quality include the existence and the presence of phytoplankton and zooplankton, the percentage of oxygen, the percentage of nitrogen dioxide and nitrogen catabolic, the ammonia, the droppings, the percentage of pH and salinity, the bioaccumulation of heavy metals, dioxins, and biphenyls. Nowadays, in most aquaculture sites, the quality of water is still performed periodically with on-site measurements. These water parameters are traditionally measured by technicians employing handheld instruments, and consequently the sampling frequency is relatively small. In some cases, the sampling interval can be of hours, during which serious hazards are not detected, with possible serious consequences on the health and quality of the fish production. Without a sufficient amount of data, technicians could not understand the causes behind the problems, thus reducing the possibility of avoiding the occurrence of the same issues in the future. An autonomous monitoring system capable of providing good measurements at a sampling interval of seconds or minutes would allow more accurate planning of the farming activities. The main purpose of this paper is to build a low-cost, do-it-yourself proof of concept of a smart buoy capable of autonomously monitoring by spectrophotometer some of the relevant parameters to evaluate the quality of water at sea and to deliver the observed data to the cloud over a long-range wireless link connected to a gateway. We have used in this experiment setup an Arduino controlling an AS7265X LED spectrophotometer. It's an amazing field of study, and the Spark Fun Triad brings what used to be prohibitively expensive equipment to the desktop. The AS7265X should not be confused with highly complex mass spectrometers, but the sensor array does give the user the ability to measure and characterize how different materials absorb and reflect 18 different frequencies of light. The triad contains a white LED, an ultraviolet LED, an infrared LED mounted alongside the sensors. These LEDs were chosen to illuminate the target with the largest swath of visible and invisible light. The LEDs are individually enabled with software configurable drive current. Our experimental setup is shown in the figure, where a spark-fun triad spectroscopy sensor is interfaced with an Arduino via an I2C protocol. This spectrophotometer combines 3 spectral sensors together with visible, ultraviolet and infrared LEDs to illuminate the surface and detect the reflected absorbed wavelengths and their intensity from 410 nanometers to 940 nanometers. As you can see, the spectrophotometer is set inside an IP68 box, which is completely waterproof and impermeable to water. The board also has multiple ways for you to illuminate the object that you are trying to measure for a more accurate spectroscopy reading. The smart buoy will be equipped with this couple of devices in order to monitor water quality. Smart buoy will be used as the device to monitor aquaculture water quality by equipping it with a spectrophotometer, which allows us to observe multiple parameters related to water quality with a single instrument. The choice of a spectrophotometer is motivated by the fact that, at least in principle, we can monitor multiple parameters by a single sensor. In the classical approach, the spectrophotometer is used to infer the absorbance or reflectance of materials and thus infer its concentration applying the Beer-Lambert law. Each type of molecule or atom reflect, absorb, or emit electromagnetic radiation in its own characteristic way. Spectroscopy uses these characteristics to deduce and analyze the composition of a sample. The main purpose of the in-lab performed experiments is to acquire experience on the operation of the spectrophotometer and having a first validation in a controlled environment the reliability of the selected device. By graphically reporting the recorded values of wavelength and intensity of absorbed radiation, the absorption spectrum of the examined substance is obtained. The correct classification of composite organic and inorganic materials in seawater is a complex task. For monitoring water quality, it is required the employment of inexpensive, commercially available reagents. However, for the sake of simplicity, in our in-lab experiments, we simulate those reactions with an increasing concentration of dye color. More specifically, in each trial of the experiment, the tank was filled with 2 liters of water. The experiment consists of an increasing number of teaspoons of a given color added and mixed in the water sample. The tank was closed during the measurements to avoid the presence of external light. The figure shows the result of the experiment performed adding up to 5 teaspoons of red dye into the tank. The wavelength of orange red is between 600 nanometers and 700 nanometers. Observing the results of these experiments, we can notice that the wavelengths around 6 and 20 nanometers show a linear correlation between the measured intensity and the percentage of red in the solution. A key aspect of any IoT deployment is energy consumption. In this section, we focus our analysis on the energy consumption of the spectrophotometer. The figure shows the energy consumption of the spectrophotometer obtained thanks to the INA 226, which is a current, shunt, and power monitor, when LEDs are switched on every second. During the active period, the consumption is about 60 milliwatt for 200 milliseconds. For the remaining 800 milliseconds, the consumption is constant at about 30 milliwatt. Consequently, the average consumption is 24 milliwatt per second. Assuming 12 measures each day and sleeping mode in the remaining time, the consumption per day is about 432 milliwatt. We illustrate the proof of concept of a smart buoy equipped with a spectrophotometer to evaluate water quality parameters in real time and capable to transmit the observed parameters to a control unit. The buoy will be typically deployed in marine environments, in the proximity of fish farms, and in general, in locations potentially not in close proximity to coastal areas, and thus it should be capable of transmitting wireless data to a gateway on shore, consuming minimal amounts of power to maximize the operation time. Our POC relies on LoRaWAN technologies to meet the low power, long range requirements of the system. The upper part of the buoy is equipped with 2 mini solar panels and a LoRaWAN 868 MHz antenna, an Arduino compatible SparkFun Blackboard C, the BL072Z LoRaWAN board, the TP4056 lithium battery charger module, and the lithium rechargeable battery. The Arduino compatible board governs the monitoring activities performed by the spectrophotometer and forwards the acquired data to an STM Micro BL072Z LoRaWAN 1 in charge of delivering the data to a gateway. The data on water quality collected by the smart buoy are finally delivered by the LoRaWAN network to a gateway connected to the FINS network via a Wi-Fi connection. The buoy is mainly powered by a rechargeable battery, but also a small solar panel is installed on the top of the buoy to provide some support in terms of solar energy harvesting. Energy consumption is the main concern since, once deployed at sea, the smart buoy is hermetically sealed and left unattended for long periods of time without the possibility of intervention. As you can see from the figure, the buoy has been actually deployed at sea, proving that the design is robust enough to run in the still sea environment. This work demonstrates the feasibility of a low-cost proof of concept of a smart buoy to monitor the quality of water in IoT deployments. The total cost of material comprising smart buoy manufactures and electronics is €415. The sea deployment is the preliminary necessary step to future measurement campaigns aiming at collecting real-time in-field data. The design has to be further refined, and some work is still needed to make the buoy more resistant to the sea environment. As an example, during the deployment was experienced some issues related to the quality of electronics wiring. However, we do believe that most of such issues can be easily resolved in our final design. Thank you for your attention.